So now we're going to continue talking about sets, and we're going to focus in on set operations right now. So there were a couple different set operations we talked about. The first one being union, which we denote by AUB. And it's all the elements that are either in A or in B. So in terms of our Venn diagram, the union would be shaded everything in A and everything in B. So both circles would be filled in. We also had the intersection, A intersect B. So the intersection is just the elements that are common to both A and B that they have in common. So it's only going to be the middle part. So the third is the set difference, or just sometimes it's just called difference, A minus B. And so this is all the things in A, all the elements in A that are not in B. So if I shade this one in, it's everything in A that's outside of the B circle. And the fourth one is the complement, A bar, or sometimes it's written as AC. It's everything in the universal set U, that's not in your set A. So it's everything outside of your set A. So what was nice about having Venn diagrams is that it was easy to compare two different sets and see if they were the same, were the same set or not. So let's look at an example. Let's say draw the Venn diagram for A intersect B complement. So we have two sets we're dealing with here. Here's A, here's B. So I'm going to first shade in the set A. Now I'm going to shade in B complement, which is everything outside of the B circle. And then I'm taking the intersection, so I'm looking for where these two colors overlap, where these two shadings overlap. So they overlap inside of the A circle, but outside of the B circle. So it would be this part right here. Well, we've already seen that shaded in part before. This was the same thing we got back when we were looking at set difference. So now we can hypothesize that we believe that these sets are equal. So we have what I'll call a conjecture, is that A intersect B complement is the same thing as A minus B. So now let's prove this. So prove A intersect B complement equals A minus B. Well, you're trying to show two sets are equal. So the way we do that is by showing that they are subsets of each other. So there's two parts to this proof. I'll say proof. Let X be in A intersect B complement. That means X is in A and X is in B complement. Since X is in B complement, that means X is not in B. So we can conclude X is in A minus B since x is in A and x is not in B. So we just showed that A intersect B complement is a subset of A minus B. And now we need to do the reverse. So you're going to let x be in A minus B, then x is in A, and x is not in B. Since x is not in B, that means x is in B complement. Therefore, x is in A, and it's in A intersect B complement, since x is in A and x is in B bar. Thus, we've shown that A minus B is a subset of A intersect B bar, B complement, and we've completed our proof. We've shown that these two sets are subsets of each other, which means that they must be equal. So then we also talked about unions and intersections of more than one set. In particular, we talked about indexed collections of sets. So let's look at an example here. So find, or so I'll say determine that the union and the intersection for the following. So I'll just write the sets up here actually. Just to save a little space, we'll put it right here. Determine negative 1 over n to 1 over n. So here, these are intervals. And so we're going to start by looking at some of these intervals. So we started off with n equals 1. And we get negative 1 to 1. Everything between here, but not including your endpoints. If n equals 2, we have negative 1/2 to 1/2. Everything between, not including the endpoints, n equals 3. You get negative 1/3 to 1/3. So everything in between, not including the two endpoints. So here, if I'm looking at finding the union, what I notice is these intervals are getting smaller, and in particular, they're subsets of each other. So, like for example, this second set, it's a subset of the first one. This one, it's also a subset of the original one. So as I'm going down, I'm noticing, for example, A3 is a subset of A2, is a subset of A1. So what's happening is these intervals are shrinking down. So this means that when I take the union from, sorry, this should have been n equals 1 to infinity. to infinity, n equals 1 to infinity. So here we're getting, for the union, we would get the interval -1 to 1. Now in terms of the intersection, if I look back, what do these sets all have in common? They're all kind of shrinking in towards 0. They're getting closer and closer to 0. So the intersection here will just contain 0, and that's it. Now I'm not going to go into the proofs of these, that these are equal. You have to show that, to show that these are equal, you'd have to show that they're subsets of each other, just like we did in the last example. I'm not going to do that here, but you should look back at our earlier examples in this section.